Hello and welcome to Lecture 6, where we're going to be discussing electrical power. This is our sixth lecture in our exploration of electricity and ultimately electricity and magnetism. At this point, we have defined things like capacitance, we've defined charge, electric field, voltage, and most recently, resistance through Ohm's law. Now, this lecture here is very much a continuation of the ideas we presented in Lecture 5 on Ohm's law. So let's look at what our objectives are. We want to appreciate that we focus on electrical power as power generated by converting, energy conversion, electrical potential energy into heat. Okay, this is the same electrical potential energy that is equal to a volt times charge. Okay, V times Q. Right, wonderful. So I bring that up because there are other forms of electrical power. Just the process of putting energy into a capacitor is the flow of energy. So charging up a capacitor would be electrical power. And we'll touch on that very idea in a couple of lectures. But for now, we're only talking about turning electrical potential energy into heat through a resistor. All right. Now, to be fair, that is really the most common application of electrical power. When we talk about electrical power, we're often talking about turning energy into heat via resistor, whether it's a heater or a toaster or a light bulb. There's so many common examples of resistors. I suppose, to get ahead of ourselves, the other really most common type of electrical power is that of an actual motor, but that does require magnetism, and we're certainly not there yet. So to get back on track, let's look at our next objective. We want to learn common expressions for electrical power. There are three of them. They're right down there. We'll talk about them in just a moment. And we want to familiarize yourself or ourselves with the kilowatt hour, which is a unit of energy. Okay, you look at it, you might see the word watt and think it's a unit of power, but it's actually a unit of power times time. And since power is energy over time, power times time is just back to energy, right? Case in point, power over time times time, the time cancels, and we're just left with energy, E for energy, okay? All right, so let's look at our key formulas. So P is power, okay? Electrical power. And, excuse me for a second, there we go. Electrical power of a resistor, okay? Notice I'm using a cursive P. This is supposed to be evocative of the script letter for E for the electromotive force. Kind of call attention to the fact that we're talking about electrical power. You can just use normal P as well, like you would for, say, the power in a mechanical system. But anyway, it's P for power, okay? This is converting electrical potential energy into heat. It is equal to current through a resistor times the voltage across the resistor. That's what electrical power is. It's the flow of charge and how far the charge is decreasing in voltage. Because essentially, the resistor, okay, represented like this, we have some charge going through that resistor. It's going downhill in terms of the voltage. Okay, the voltage drops across the resistor. That decrease in energy per charge gives us our power, as long as we know how much charge per second is actually falling off of that drop, going down that elevation change, which the voltage represents, okay? So it makes sense that current times voltage, both through and across a resistor, is equal to the power that that resistor converts, okay? All right, you could also think of it as the power that the resistor outputs. Now, due to Ohm's law, which you recall is V equals IR, we can either substitute out the V from our expression, or we can substitute out the I from the expression. If we want a power where we've eliminated the V, so we have a power that is dependent only on the current and the resistance, then it looks like this. It's I squared times R. That would, of course, be the current through the resistor squared multiplied by the resistance of the resistor in ohms. Or we can have an expression that is completely independent of current, where it's just the voltage drop across the resistor squared divided by the resistance, okay? So this has some really interesting consequences. So for example, if you have a fixed current, then the greater the resistor, the greater power. On the other hand, if you have a fixed voltage, the greater the resistance, the less the power output. That's quite interesting, right? And it's more common in everyday circuits to have a fixed voltage. Batteries supply a fixed voltage, power outlets supply a fixed voltage. There are exceptions. The most notable exception is a solar panel, which produces a fixed amperage or current as opposed to a fixed voltage. But definitely the most common that you'll see, and you'll almost take it for granted, is fixed voltage. So you'll think of resistance as being something that decreases power. As resistance goes up, power goes down. Okay? All right. But again, to be fair, that is only for a fixed voltage. By fixed, I mean unchanging. Okay? Like you plug something into the wall, it's 110 volts. It's always 110 volts. Okay? Unless you convert it, and you can convert it. You can convert the voltage. We'll talk about that when we talk about transformers. But again, that requires magnetism. So can't get ahead of ourselves, right? But and again, the label here is just labeling that R is resistance of the resistor measured in ohms. All right, and our other only equation here is just the definition of the kilowatt hour. The kilowatt hour is a unit of energy. It is a non-base unit of energy, kind of like the calorie, okay? Still a metric system unit, but not exactly equal to a joule. A joule is the only base unit of energy. Kind of like the horsepower is a unit of power, but it's not the base unit of a watt. Same idea here, okay? And by the way, the units of the power would be in watts. So 1 kilowatt hour is 1,000 watts, so 10 to the 3 watts, multiplied by the number of seconds in an hour, which is just 60 squared, and 60 squared is equal to 3,600. You see this a lot when I do time conversions, okay? So it's number of seconds in an hour. And that gives us 3.6 million joules. So that's what a kilowatt hour is, 3.6 million joules. And why on earth would we care about something called the kilowatt hour? Well, that's the way every single utility bill in the United States is given to you in kilowatt hours. That's the unit you pay for in energy. So it has a very nice application for actual utility costs that we're all familiar with in our everyday lives. Okay, so let's look at the types of problems we're going to see in our practice. Type 1, simple problems that involve using the equation for electrical power of a resistor. And any of these, by the way, any of the 3 types can involve a kilowatt hour question. Type 2, fairly complex problems that involve electrical power for resistors of specific dimensions, resistivity, and temperature. Okay, so this is going to be using the parameters of the resistor. Type 3, fairly complex problems that involve relating electrical power to other heat energy. Okay, may include conductive heat flow, radiative heat flow, or specific heat or latent heat. Okay, and so you'll notice there's a lot of terms there that are all included in a thermodynamics chapter or chapters. And so if you need to review ideas, I make sure to include the keywords here, like conductive heat flow, like radiative heat flow, and the associated equations. But if you need to review what specific heat is and how it's different from latent heat, okay, hint, latent heat has to have phase changes, specific heat has to have temperature changes, then you need to go back and look at notes, such as my notes, my lecture notes, and my associated videos on thermodynamics, okay? All right, so let's take a look at our first example, type 1. If a 500 watt heater carries a current of 4 amps, what is the resistance of the heating element and the voltage drop across it? Okay, so here we're going to set up the equation power equals I squared times R. Okay, because I was given a current and I was asked for a resistance, so it makes sense to use that formula. So if I go ahead and solve for the resistance, I get a resistance of 31.3 ohms. Okay. Now, I actually went ahead and only solved for the resistance here. If we want to find the voltage drop, it would simply be a matter of using V equals IR, which then would be 4 amps times 31.3 ohms. It's just Ohm's law. And so that would give us a voltage drop of about 120, about 120 volts, okay, approximately. But again, I didn't include it here. I'm going to need to do a revision on this anyway, so I'll include it when I upload these notes. Okay. Now I do want to do a unit check here because you may be really kind of getting overwhelmed with the idea that power, which is wattage, which is of course joules per second, that's equal to things like current and resistance. After all, the ohm is an odd unit. Like how do we even relate these things? So let's make sure we can actually justify that these units hold up. So what I'm going to do is I'm just going to consider this relationship right here, that resistance is equal to power divided by current squared, okay? So resistance is a volt per amp. We know that from Ohm's law, V equals IR. So if I solve for R, that's V over I, okay? That's volts per amp. It's a good way to think about what is resistance, the volts per amp, the voltage per current. Okay, then power, of course, is joules per second. And then I'm dividing by current squared. So here I just multiply by 1 over amps squared, okay? And I just did this to kind of clear up the expression here, okay? Then let's continue this, all right? So remember that the volt is the joule per coulomb. okay? Volt is energy normalized by charge. It's energy divided by charge. The unit of charge is the coulomb. So all I've done here is replace V with the joule per coulomb, J over C, okay? The A for amps is still around on the left-hand side of the equation. Now, what have I done over here on the right-hand side of the equation? Well, I've left my power expressed in joules per second alone, and I've taken my amps squared and I've split them up. One I just left as 1 over amps, okay? But the other one I expressed as coulombs per second. But since it's in the denominator, it would be 1 over coulombs per second. And the reason I can do that, of course, is because an amp is charge per time. Okay, current is charge per time. It is the coulomb per second. Now, that means that we can show equivalence with units because the seconds cancel. After all, we have a seconds in the denominator and a seconds in the denominator of the denominator, so these two cancel. Then we're just left with a joule over a coulomb times an amp, which is exactly what we have on the left-hand side. Okay? So indeed, the units make sense. Now, I didn't break these all the way down to base units. Okay, these are still derived units. I could break them all the way down to kilograms, meters, and seconds. And then I could even express them in terms of the dimensions and do dimensional analysis. But I wanted to do the quickest version that hopefully is convincing that these units make sense. And if the units make sense, everything else will. If the units don't make sense, you have no hope of any of these other ideas making sense. Okay, so make sure you review the units. Okay, part B. So part B, energy is power times time. All right. And after all, in part B, I should be clear here. The question asked, if this heater is run for 2.5 hours, then how many kilowatts of energy does it dissipate? Okay, which is, I could say, convert, right? But it's dissipating it from potential to, heat energy throughout the room. Okay, so we're going to just take the wattage here, 500 watts, multiplied by the time, okay, which is just 2.5 times 3,600 seconds, this number of seconds in an hour. And then I have my conversion factor, because I'm going to take joules per kilowatt hour, because this expression here is in joules. So I have to divide by something that has units of joules to cancel out the joules, okay? Because watt seconds are joules, cancel them out, and then I'm left with kilowatt hours in the denominator of the denominator, which is the same as the numerator. So my final answer will be in kilowatt hours. Okay? So in other words, if you want to convert from joules to kilowatt hours, you just divide by 3.6 million every time. Divide by 3.6 million. Okay. And so we get 1.25 kilowatt hours. Not a lot of kilowatt hours because, well, after all, a kilowatt hour is a lot of joules. So it makes sense it's only a small amount. Okay? All right. Now, part C, how much does it cost? Okay? Well, the cost is 16 cents per kilowatt hour. And if I am using 1.25 kilowatt hours, well, that's just 20 cents. Okay? This is 1.25 of that rate. All right? So you pay 20 cents to run this heater for 2.5 hours. Now you want to know something? This is actually a really realistic number. This is about what we pay in Contra Costa County for kilowatt hours. Okay? All right, neat. All right, example 2. Light bulbs are usually listed by their wattage, which assumes a voltage source of 120. Okay? 120 volts. That comes from the wall. All right? Based on this, which has a larger resistance, a 60-watt light bulb or a 100-watt light bulb? What do you think? Which is a higher resistance? Okay, let's see. Okay, so here's the other typo I'm going to have to fix. Here I wrote W equals V squared over R, but of course these are all the variables representing these expressions. These are not units. When I wrote W, I was thinking watts for power, but I'm not writing this in terms of its units, I'm writing in terms of variables. So I should be using P. So this should be a P, not a W, because this is not work, which W implies, it's power. Again, I was just thinking watts, so I wrote W, but I will fix this. This should be a P, okay? So we have power equals volts squared over R, which is just one of the ways to express power. It's this one. There you go. Okay, fixed, and it's the good one to use when you have a fixed voltage, which indeed power from a wall would have. Okay, so then I'm going to solve for resistance, just going to cross multiply. Okay, again, this should be a P. Okay, so now we can actually plug in our values in terms of watts. Okay, so the resistance for the 60-watt light bulb will be 120 volts squared divided by 60 watts, which gives me 240 ohms. On the other hand, the resistance for the 100-watt light bulb is 120 volts squared divided by 100 watts, which gives me a resistance of 144 ohms. So that's it. The higher wattage light bulb has lower resistance. Okay, as we continue to lower the resistance, we would just get higher and higher wattage. Okay, for a fixed voltage like this. And then the difference is just 240 minus 144 is a difference of 96 ohms. Okay, all right, looks good. All right, let's move on to our next type of problem. Okay, consider an old tungsten light bulb, which is really what we were talking about in the previous example, example 2. Okay, and old because as a society, we've moved on from tungsten light bulbs rather quickly, and now we generally use LED light bulbs, although compact fluorescents are also used. Okay, so consider an old tungsten light bulb. The wattage is listed as 65 watts when connected to 120 volts. But that is when its operating temperature is 2,450 Kelvin. Now that's actually a really good point because they're rated at a certain wattage, but they're rated at a wattage that corresponds to how hot that metal is when it's glowing hot. Okay? Okay. Well, when the bulb is first turned on, how much greater is the amount of power that the bulb draws for the first moment when the bulb is still at room temperature, 393 Kelvin? Okay? So the idea there is should be 293. I think I used 200 in the actual equation, so we'll check that. But it should be 293 because 273 Kelvin is equal to 0 degrees Celsius, which means that 293 Kelvin is equal to 20 degrees Celsius, which is room temperature. So I think that's just a typo in the problem, which I can easily fix. But we'll see what calculation I made because I may have to adjust the number accordingly. But anyway, I don't want it to be 393. I mean, it could be 393 because it heats up fast, and it's going to heat up to an operating temperature of really, quite hot very quickly. But we want it the moment it's turned on. So I would prefer this was 293. Okay, and then we're going to take the resistivity of tungsten at room temperature to be, and this is, you look it up for common resistivities. It's a material specific value, 5.6 times 10 to the negative 8 ohm meters, and the thermal coefficient we're going to take as 4.5 times 10 to the negative 3 inverse Kelvin. Okay, the thermal coefficient is that it is used in the expression explained in lecture 5, where we talk about how resistance is dependent on temperature. Okay, because resistivity is dependent on temperature. Okay, so let's see how we'd approach this problem. So the first thing we do is we just write the same expression we used a couple times, power equals voltage squared over resistance. Okay, so we have a 60 watt light bulb. We've got 120 volts, so then we can find the resistance. This is basically the same, the start of this is the same as the previous example. So then the resistance, all right, at a temperature of 2,450 Kelvin is 220 ohms. Okay, so at its operating temperature, it is 220 ohms. We haven't used the temperature yet. Notice that's, but if we just say, okay, well, it's rated at 65 watts. It's rated at 65 watts with the assumption that's the temperature. That's why we don't need to actually calculate anything involving the temperature yet. Okay, so it's a 220 ohm resistor. Okay, all right. So now let's find out what happens when it's cool, or at least much cooler. So what we're going to do is consider this ratio of the initial resistance over the operating resistance. Okay, now the initial resistance is just going to be rho naught. Now why is that? Well, because if you think about this expression, here's the expression for temperature dependent resistivity. Well, you consider that, right? This rho equals rho naught times 1 plus alpha times T minus T naught. Well, if you recall from lecture 5, what is T naught every time? T naught is 293 Kelvin. So if your T is equal to T naught, then this whole expression cancels out. It just becomes 0, all right? Which means that rho just becomes rho naught, which is why the numerator can simply be rho naught. On the other hand, when it's hot, when T is not equal to T naught, then this parenthetical expression survives. It doesn't just cancel out. And then right here, L over A, well, that's of course because the actual formula for resistance is rho L over A, but we never changed the length or the cross-sectional area of the tungsten filament here, so it's not relevant for the problem. Okay, so they cancel out. Okay, so then we can go ahead and solve for R naught. That's the resistance of the tungsten element when it is first turned on and it's still at room temperature. Okay, so you see here, right, we have the operating resistance, which is R, not R naught, because it's not where it started. This is R is the final resistance. R naught is the initial resistance. All right, okay, and then we've got the the coefficient, the thermal coefficient, okay, 4.5 times 10 to the negative 3 inverse Kelvin, and then we have the temperature difference. And here I did use the correct T naught, 293. So the only typo is here in the body of the problem. That should just say 293. but the right value is used here, okay? So that means that the resistance when it's first turned on is 20.7 ohms, okay? Significantly less resistant, okay? Resistive. But that makes sense because as things get hotter, as a metal gets hotter, it resists the flow of electrons more and more, okay? It becomes a bigger resistor. So when it's hot and has been running for a while, its resistance is 220. When it's first turned on, its resistance is about a tenth of that. It's only 20. Okay, both ohms. All right, so we're almost there. So that means we can find the initial power as V squared over the initial resistance, okay, which is just 120 volts divided by 20.7 ohms instead of dividing by, well, 220, okay? And that means our initial power is 696 watts, okay? So let's appreciate that because that means our light bulb here, which normally draws 65 watts, that's how much energy per time it's consuming, okay? Well, when it's first turned on for the first second or so, right, maybe a fraction of a second, it's drawing 696. And then for a while, right, it's going to take, I mean, it takes a while for a light bulb to get full temperature, right? So let's say at least a minute until it's all the way heated up. Well, that means it's still going to be drawing more power. It's going to eventually reach this value and stay at it, and only draw, why I should say this value, reach that value of 65 watts and stay at 65 watts for as long as it remains on. But at first, it's drawing significantly more power, which means it's less efficient. Okay, so what that means is that any device that is based on a resistor, you're going to be using a lot more power if that device is being turned on and off a lot. Okay, it actually significantly more power, because as it heats up, it's going to be using less power. Pretty neat, right? So you could actually have a measurable difference in your utility bill if you flick the light bulb on and off, as opposed to just leaving it on all the time. Okay? All right, example 4. All right, so example 4 is going to involve, unlike example 3, which is type 2, example 4 is going to be one of those type 3 problems that's going to involve more specifics about heat flow. So this is where we're going to see material that does require reviewing the topics of thermodynamics, okay? So in this first one, it's going to be all about specific heat. Okay, but I'll lay out how it's connected. So consider a large lattice work of copper wires used for heating in a factory. If all the segments have a radius of 7.15 millimeters and a total length of wire of over a kilometer, then how long will it take the wires to warm up to an operating temperature of 400 Celsius when connected to a 110 volt power supply? So the idea is you have this like huge lattice work of wires. They're all connected. They all come from one power supply, and you're heating it up. You're turning it on, and you want to wait for it all to warm up, okay? So assume all the initial energy converted by the resistor goes to warming the wires, and that the starting temperature is room temperature, in other words, 20 degrees Celsius, in other words, 293 Kelvin. Take the average resistivity of copper as 1.68 times 10 to the negative 8 ohm meters. Take the density of copper as 8.96 grams per cubic centimeter, and the specific heat of copper as 0.385 joules per gram degree Celsius. Okay? All right, so let's tackle this problem. So we're going to start the same that we did the last couple ones. Define power as a volt squared over resistance, okay? And then solve, well, we'll do substitution, but we'll express resistance as resistivity times length over cross-sectional area. This is the resistance of a wire, right? Totally appropriate since our lattice work is made out of wires with a known length and a known cross-sectional area, all right? And a known resistance for that matter. And then we'll substitute R into our expression for power. That's all I've done here, okay? And then we'll just solve for it. So this is the power output of the lattice. Now, at this point, that power isn't going anywhere. It's still just heating up the lattice. Now, if you stop and think about that, that means sort of this is the initial process of the lattice. After it's heated up, after it reaches 400 degrees Celsius, the idea is that then that power then starts dissipating somewhere else. It maybe starts heating up a room or heating up a chamber or maybe heating up a vat of metal or something. Whatever it's used for, okay? And also, this assumption that I say, assume all the initial energy is converted by the resistor goes to warming the wires. That means that none of it is actually being conducted away from the wire. None of it is being radiated away from the wire. It's the energy is kind of making its way throughout the actual thickness of the wire and hasn't actually started dissipating away from it yet. Okay. Now that wouldn't happen. You'd have some of it leaving as it's still warming. and you have to deal with that effect, the surface to volume ratio, and all these difficult things to estimate. But here we can make an assumption that at first all the energy is just going to the internal energy of our metal, our lattice work of metal wires. Okay, so there's our power. Okay, and when we do that, we find out that it's 9.72 times 10 to the 4 watts, so 97,000 watts. Okay, it's a big number because it's a lot of wire. Okay, it's a lot of wire, so it's a lot of power. Okay, all right. All right, and the lattice mass, okay, so why, well, you'll see in a second why we need the mass, okay, but it has to do because the fact we need to heat it all up, so we need to know how much of it we're heating. So the mass of the entire lattice would be its density times its volume. Now notice here that we've got rho to represent resistivity, which is standard, but then here rho, the Greek letter, also is usually used for density, kilograms per cubic meter. So I added the subscript m to show that this is a mass density to differentiate it from rho for resistivity. Okay, V is just volume here, which I suppose is confusing because we also have V for voltage. Nah, we don't have enough letters, right? But anyway, here are the values. So the density converted from grams per cubic centimeter to kilograms per cubic meter is 8,960. The reason I want to convert over is because I want everything to be in standard units. Okay, then I have pi times, well, r squared, because I'm finding the volume of a cylinder, which is going to be the area times the length. Okay, so the cross-sectional area times the length. And this is just the 1.19 kilometers, okay, just as showed up here, okay, the same length, okay, and that gives us the total mass of all that wire is 1,710 kilograms, okay, and then, so the energy to heat it is Q for heat, equals C times M times delta T, okay? This is a specific heat formula, all right? C is the specific heat of copper, M is the mass, delta T is the temperature change of the copper, okay? So the Q to heat this much copper, all right, is the specific heat, 385 joules per kilogram Kelvin. Again, I converted over from joules per gram to joules per kilogram, times the mass of all the lattice work, times the temperature change. Now the temperature change went from starting at 20 and ending at 400. So that was a 380 degrees Celsius temperature change. But here, notice I'm using Kelvin. The reason I'm doing that is because I want us to be reminded when we're thinking about heat and inevitably how heat is related to things like resistor heaters, that a change of 1 degree Celsius is equivalent to a change of 1 Kelvin. So it doesn't matter if my units are Celsius or Kelvin. Okay? Okay, so it's just 380. That's my temperature change. All right, and so then that gives me the amount of heat to heat up that metal, that many Kelvin, is 2.51 times 10 to the 8 joules. All right, so 251 million joules, a lot of energy. Okay, so then we say, okay, well then going back to the relationship that power is heat over time, all right, and here Q is being used for heat, but of course Q is an energy, okay? So I could write E, but it's standard to use Q to represent heat, okay? So then if I solve for T, because after all, this example was asking for how long does it take this lattice work to get up to operating temperature, all right? So then T is just Q over P. Now I can put everything together, all right? This is the time to heat the lattice. So then T is going to be the total amount of heat necessary to heat the lattice divided by the amount of energy per second that actually flows into the lattice due to its resistive properties. And we get 2,580 seconds, which is 43 minutes. Okay, great. Of course, it would in reality take longer. This is a lower estimate because it's not going to be containing all that heat. Some of it's going to be lost. Okay, so it will reach operating temperature eventually. You know, depending on its surface properties and how it's radiating heat or conducting heat into the external environment. But this is a good lower estimate, and it's good to have at least some lower bound on a calculation like this. Okay, all right, let's do our final example. Now, this final example is a nice continuation of some of the ideas we just saw in example 4, because here we're dealing with a system that isn't just heating up, but now is at equilibrium. We have a system that has already reached its operating temperature, and it's just going to continue there. But in doing so, it has to have an equilibrium. There has to be as much power going in as power going out, which is a cool idea. So let's think about it. So now we have a silver wire. We've replaced our copper with silver. It's much shorter. It's only 5.52 centimeters long. Okay, so maybe it's part of some heating device or something. It has a very small radius of 124 microns or micrometers, and it's connected to a 65 millivolt battery, so very, very tiny voltage source. Okay. All right. What will be the final equilibrium temperature of the wire's surface if we assume that all of the energy that the resistor is converting is being transferred away via radiative heat flow? Okay, and this is a key term right here. There's a formula for radiative heat flow. We're going to use it. Okay, we'll take the average resistivity of silver to be 1.5 times 10 to the negative 8 ohm meters, a density of 10.49 grams per cubic centimeter, a specific heat of 0.240 joules per gram degree Celsius. All right, and we'll take the operating emissivity of the wire to be 0.205. Okay, and we're actually not going to use the specific heat, come to think of it. I'm not sure we use the density either. Let's think about, no, we don't. So we're not, I think this is just included information because I was modeling it off the last one, but it's not going to come up. We will not need the specific heat nor the density, although these are the correct values for silver. Okay, all right, but we're definitely going to need this number, or this emissivity. Okay, so what does it look like? So first define the energy converted by the resistor. Okay, this is just the potential energy to heat. Okay, so we'll start the way we started the last four problems, right? We'll say the power of the resistor is just voltage squared over resistance. And again, that's because, again, we have a voltage source, okay? So prevalent, all right? And so then we have a voltage source divided by the resistance, which we'll express as resistivity times length over cross-sectional area, okay? Great, well, we have all those quantities, okay? So let's plug in our numbers. Notice here's the resistivity, here is the length, and the cross-sectional area is using the radius, okay? And there's our very small voltage. So we'll end up with the small power, 0.25 watts, a quarter of a watt, quarter of a joule per second, okay? And the radiative heat flow is this equation right here. Hopefully this looks familiar. If it doesn't, you do have to review. This is the formula for radiative heat flow. So this is any object that is radiating energy away as light, okay? And it's emissivity times a constant of the universe called the Stefan-Boltzmann constant times the surface area of that object that's radiating light, the surface temperature to the fourth power minus the surrounding environment's temperature to the fourth power. Often you'll see this equation for like planets or stars, in which case T2 is 0 because it's in the vacuum of space. But in this case, it's not. It's in a room with a temperature of 20 degrees Celsius. Okay. All right, and we're going to set the two values of power equal to each other. Why? Because we have an equilibrium situation. There's as much power going in as power going out. The power going in is this power. The power going out is that power. Okay, so power going in because of the conversion of electrical potential to heat. Power going out as radiative heat, because there's other things heat can do. We just saw an example for. Heat can actually change the internal energy of the wire itself. But we're done there. The internal energy has reached whatever it's going to do. We have an equilibrium situation, which means the wire can't heat up anymore, which means that with the power, the energy has to go somewhere. It can't just build up. You can't have a bottleneck of power. And so it's all going in the environment as photons, which are particles of light. More on that much later. Okay. Okay, so here we go. Setting the two powers equal to each other because of the equilibrium condition. Equilibrium condition. All right, so there we have the power we solved for, just the value of it. And here I'm just plugging in my values. So my emissivity is 0.205. There's no units on emissivity, okay? And by the way, quick review of emissivity. Things that are like totally shiny have an emissivity of 0. That means that they're reflectors, which also means they're really bad emitters. They can't actually emit energy. Something that is a black body, so something that has totally black surface, has an emissivity of 1. That's a perfect emitter. Okay, it's very good at radiating away energy. Okay, in this case, because it's a metal, we have something that's kind of on the low end, not particularly good at radiating energy away. Okay, but 0.205, excellent. There is our Stefan-Boltzmann constant. Okay, all right, and here is our cross-sectional area. Our cross-sectional area is just going to be the surface of basically a rectangle that is, so we're basically excluding the end caps of the wire. I mean, they'd be so small anyway. But so we're essentially, we imagine like folding the wire out, and then we have 2 pi r, which is the circumference times the length. And so that's the rectangle that you see expressed right here, okay? And then multiplied by the surface temperature to the fourth power minus the surrounding environment temperature to the fourth power. And here, it's super important that you have to convert from Celsius to Kelvin, because this formula right here only works for Kelvin, all right? It does not work for Celsius, because obviously cubing or raising a number to the fourth power, it depends if it's 20 or if it's 293. You'll get very different numbers. Okay. So then it's just a matter of solving for t surface. All right. So I've done the algebra here. It's quite straightforward. I just take this whole value here and I divide it by both sides. So I just get the value in watts divided by those leading numbers. And then I add 293 to the fourth to both sides because I'm trying to isolate t. Okay. And then I take that whole expression, which you imagine all would be on the left-hand side, and raise it to the 1/4 power. Because when you have x to the fourth power raised to the 1/4 power, you just get x, thus having isolated t surface, the value I'm trying to solve for. And we get 844 Kelvin. Okay? Well, since everything else was given in Celsius, we should probably give the final answer in Celsius. So to convert this over to Celsius, we just subtract 293, and there we go, 571 Celsius, which luckily is well below the melting point of silver, so that would actually work. You wouldn't have to worry about this wire melting. And that's actually a really good point, because if this wire had different dimensions, if this wire was connected to a different voltage source, then there is no safe operating temperature, because once it reaches a heat flow equilibrium with the surrounding environment, its surface temperature is too hot and it starts burning and melting. And that happens when you run too much voltage through a wire and it can't handle it. Okay? It's exactly the kind of issue when you burn up a circuit. All right, but there we're not, 571 Celsius. Okay. So hopefully these few examples talking about electric power have been informative and helpful. And thank you so much for watching this video.